Hi everyone, this is Mrs. J, and today we're going to talk about indeterminate forms and L'Hopital's rule. Okay, I have a quick warm-up for you guys, so please pause the video and give it a try. All right, go ahead and check your work here. So first, it's important to note the domain of our original function, and because of this natural log portion, we know that the domain must be greater than 0. Just a reminder of what our natural log function looks like. So we do have that vertical asymptote, and it's only defined for values greater than 0. So to find critical numbers, we find our derivative. We know that the critical numbers occur when the derivative is undefined or 0. Although x equals 0 would make our function undefined, it's not part of our domain, so it wouldn't be considered a critical number. But we can find when our derivative is equal to 0, and that's when x equals 1. So we know that that's a critical number, so it might be where our graph changes from increasing to decreasing or vice versa. We know that sometimes maxes or minimums occur at these critical numbers, sometimes they don't. So we can do a little sign analysis with our derivative f prime of x around our critical number of x equals 1. So to the left of 1, I plugged in x equals 1/2. We get a negative value, meaning that our derivative is negative, so f of x is decreasing because the slope is negative. And to the right of 1, our derivative is going to be positive, which means that f of x is increasing because our slope is positive. So that means that we're increasing everything to the right of 1, and we're decreasing from 0 to 1 because, again, 0 is part of our domain restriction, so I'll add it in right here. So since our graph is changing from decreasing to increasing at x equals 1, we know that that is actually a minimum value, and really, I know it says relative here, this is actually an absolute minimum because our graph is going to be decreasing infinitely here, so it kind of approaches that asymptote. It actually looks like this. So it's always decreasing in this region, and it's going to increase infinitely to the right. So it looks, our f of x function ends up looking something like this. So this 0.11 actually ends up being an absolute minimum. All right, so today we're actually going to return to some limits, and we're going to learn a new concept which is called L'Hopital's rule. So this essentially helps us find a limit of the quotient of two functions where we're getting a very specific type of indeterminate, or two very specific types. So here we're assuming that f and g are differentiable functions, and then we're supposing one of the two cases. We're supposing that either the limit as x approaches a of f of x and g of x equals 0. So you essentially end up with a 0 over 0 indeterminate, or we're assuming that the limit as x approaches a of either f of x or g of x equals positive or negative infinity, giving you that infinity over infinity indeterminate. So if you get either of these specific indeterminate forms, you can actually find this limit by taking the limit of the derivative of each of the functions. So you take the derivative of the function in your numerator and the derivative of the function in your denominator, and then you try to find that limit using direct substitution. Now, it is really, really important to remember that whenever we are evaluating limits, we always try direct substitution first, because sometimes direct substitution works. But if direct substitution gives us an indeterminate, then we say, okay, is this a case where we can use L'Hopital's rule? And it only works in two, again, very specific cases. It only works for these two cases, so plus or minus infinity over plus or minus infinity, or 0 over 0. We note that there are many other indeterminate forms, so any of these other forms will not work for L'Hopital's rule. It needs to be one of these two forms, and sometimes we will actually kind of go out of our way to try to create one of these two forms so we can try using L'Hopital's rule. All right, let's try a couple together. So these two limits should look very familiar. We know that this limit is equal to 1. We know that this limit is equal to 0. But now we can actually evaluate this limit using a new method, our L'Hopital's rule. So remember, we always start with direct substitution because we need to make sure it's the right type of indeterminate. So when I substitute x equals 0, we end up with the 0 over 0 indeterminate, which means that we can use L'Hopital's rule. So I'll say LH. So what we do is we are going to take the derivative of the numerator, the derivative of sine is cosine, and we take the derivative of the denominator, the derivative of x is 1, and now we're going to try to evaluate this limit. So we could do direct substitution again, and here we just end up with 1. So that's the answer that we know to be true, but now we're able to find it in a different way. Okay, let's try the second one. Again, we should always start with the direct substitution. So if you substitute 0 here, we get 1 minus 1 over 0, which is the 0 over 0 indeterminate, so we can use L'Hopital's rule. So let's take the derivative of the numerator and denominator. So the derivative of cosine is negative sine. The derivative of negative 1 is 0. And the derivative of x is 1. So now I can try direct substitution, and that does just give me a value of 0, which again is what we know to be the answer. So just make sure when you're trying to use L'Hopital's rule that you do have the correct form of the indeterminate before you use it. Okay, let's try another one together. Again, we always start with direct substitution. So if I do direct substitution here, I get 0 minus 0, which is 0, and 0 cubed, which is 0. So we know that we can use L'Hopital's rule. So let's take the derivative of the numerator and denominator. So we get cosine of x minus 1 over 3x squared. And then we try direct substitution again. So if I plug in x equals 0, here we get 1 minus 1, which is 0. And then here we get 3 times 0 squared, which is 0. So we get another indeterminate, but this indeterminate works for L'Hopital's rule, so I can apply it again. So let's take the derivative of our numerator and denominator again. The derivative of cosine is negative sine, the derivative of negative 1 is 0, and the derivative of 3x squared is 6x. So now let's try direct substitution again. Plugging in x equals 0 gives us 0 over 0, so another indeterminate, but it does allow us to try L'Hopital's rule again. So we just keep going. So take the derivative of the numerator, so negative cosine of x over 6, and now we can try our direct substitution. The cosine of 0 is 1, so we actually now end up with an answer, negative 1 over 6. So you can see that sometimes you actually need to do a couple rounds of L'Hopital's rule. As long as you have the right form of the indeterminate, you can apply this rule until you end up with an actual limit. All right, let's try another one together. So we always start with direct substitution. So if I substitute negative infinity here, a negative infinity squared is positive infinity. And if I substitute negative infinity here, well, I end up with e to the power of negative infinity, which is like saying 1 over e to the power of infinity, and 1 over an extremely large number, this would actually approach 0. So I end up with the infinity times 0 indeterminate. It is an indeterminate, so this is an indeterminate, but it does not work for L'Hopital's rule. So we say no LH here. One thing you can try is rewriting the original function in a way that allows us to use L'Hopital's rule. So remember, we want the 0 over 0 or the infinity over infinity indeterminate. So I'm wondering, is there a way that I can rewrite one of my terms to give me a fraction? So you can actually take e to the x, move it to the denominator, and call it e to the negative x. Now if I did direct substitution, I get negative infinity squared, which is positive infinity, and I get e to the power of positive infinity because the negatives cancel out, which gives us another infinity. So for this indeterminate, we can use L'Hopital's rule. So by rewriting it in a different way, we're now able to use our new rule. So let's take the derivative of the numerator and denominator. Here we get 2x, and here we do need to use the chain rule. We know the derivative of e to any power is just e to that power. And then the derivative of negative x is negative 1. So it gives us negative e to the negative x. So that's our chain rule derivative. And now we can try direct substitution again. So in the numerator, we get 2 times negative infinity, which is negative infinity. And in the denominator, we get negative e to the positive infinity, which gives us another negative infinity. So again, we still get an indeterminate, but we can try using L'Hopital's rule again. So we don't give up yet. So again, let's take the derivative of the numerator and the denominator. And again, we do need to use that chain rule here. And the negative is disappearing because when you take the derivative of negative x, you multiply by negative 1 again. So let's try doing our direct substitution. The numerator is a constant, so it's going to remain the same. Here, if you substitute, sorry, this should say negative infinity, we get e to the power of positive infinity, which is infinity. And we know when we end up with 2 over infinity with our direct substitution, this limit is equal to 0. Because 2 divided by an infinitely large value will approach 0. So this is really just saying that this function does have a horizontal asymptote as x approaches negative infinity at y equals 0. So remember, that's what limits at infinity are really telling us. All right, let's try another one together. So here we have the limit as x approaches infinity of x to the power of 1 over x. So if we do direct substitution with infinity, we end up with infinity to the power of 1 over infinity, which is 0. So this is an indeterminate, but it is not applicable for L'Hopital's rule. It's not the right type of indeterminate. So we need to find a way to rework our function. So this one's definitely a little bit trickier, but let's say we go back to our original function. Let's say we have y equals x to the power of 1 over x. And let's say that we decided to use some logarithmic differentiation to help us approach this limit. So we would take the natural log of both sides, and we know that we can use our power rule here to bring 1 over x out front. So we have this. Now let's try taking the limit of the natural log of y. So notice that we're going to go back to the limit, but this time it's not of y, it's of the natural log of y, which we'll readdress kind of at the end of our problem. So we're going to take the limit as x approaches infinity of the natural log of y, which is the limit as x approaches infinity of 1 over x natural log of x, right, because these two expressions are equal. Now if I rewrite this, the limit as x approaches infinity of natural log of x over x, and we do our direct substitution, we end up with infinity over infinity, which is one of our indeterminates where we can use L'Hopital's rule. So we're going to do the derivative of the numerator and the denominator. So remember, the derivative of the natural log of x is 1 over x. So the limit as x approaches infinity. So we have 1 over x, and the derivative of x is just 1. So this just gives us 1 over x. And again, if we do direct substitution here, we get 1 over infinity, which that limit approaches 0. Now, it's really important to remember, again, that this is the limit as x approaches infinity of the natural log of y. This limit is equal to 0. But we want to know, well, what's the limit of this function, which was just equal to y, not the natural log of y. So if we go back down here, we're essentially saying as x approaches infinity, the natural log of y approaches 0. But what would just y approach? So if we want to get rid of that natural log of y, we could try doing this on both sides. So it's e to the power of natural log of y equals e to the power of 0. And we know that this just simplifies to y. So y would approach e to the power of 0. So y would approach 1. So we can say that the limit as x approaches infinity of y equals the limit as x approaches infinity of our original function which equals 1. So when you do this logarithmic differentiation to help you kind of rewrite your function in a form that we can use L'Hopital's rule, you have to remember that here we're finding the limit as x approaches infinity of the natural log of y. So once you find that limit, you have to do a little extra work to figure out, well, then what's the limit as y, for y as x approaches infinity. All right, let's try these last two together. So it's the same function here, but we're finding the limit as x approaches infinity and then as x approaches 0 from the right. So here, if you do direct substitution, we end up with the infinity minus infinity indeterminate. So we cannot use L'Hopital's rule yet. So we want to try to find a way to rewrite our function. And we know for L'Hopital's rule, we need some sort of fraction. So we can have 0 over 0 or infinity minus or infinity over infinity. So one thing we can try here is actually factoring out x, and then we have 1 minus the natural log of x over x. So notice I'm not factoring it out from within the natural log, but from this term I can rewrite it like this. So if you tried to do direct substitution for just this part right here, we would end up with infinity over infinity, so you can use L'Hopital's rule for just this portion of our function. So let's take the derivative of just that portion, so x times 1 minus, so remember the derivative of natural log of x is 1 over x, the derivative of x is 1, so it's like this. And then we can try direct substitution. So we get infinity times 1 minus 1 over infinity gives us 0. So it's infinity times 1, which is just infinity. So what this means is as we move to the right infinitely, we have end behavior that is unbounded. It's just going to increase infinitely as we move to the right. Now if you look at part B, we're asking what's the limit as x approaches 0 from the right. So again, the reason why we are asking this specific limit is because remember our domain here is 0 to infinity because we do have that vertical asymptote. This is that graph that we looked at earlier, so remember it looks something like this. So we know what the answer should be. So let's actually try to evaluate the limit. I know that this part, the linear function, the limit as x approaches 0 from the right would just be 0. So we know here it's equal to 0. And then for the natural log portion, if you think of your natural log function, so again, here's just natural log of x. It looks like this. We know that as x approaches 0 from the right, for natural log of x, our function approaches negative infinity. So for just this portion, our function would approach negative infinity. So we have 0 minus negative infinity, which is positive infinity, which does match the graph that we came up with earlier in the warm-up. All right, I've got one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. Direct substitution gives us a 0 over 0 indeterminate, so we can use L'Hopital's rule. Here's our the derivative of the numerator, derivative of the denominator, and then we can try direct substitution again, and that does give us a value, and you get natural log of 2 minus the natural log of 3. All right, here's one last one for you to try. So again, pause the video and give it a shot. All right, go ahead and check your work here. So when you do direct substitution to start, we get the infinity over infinity indeterminate, so you can use L'Hopital's rule. So then we can do direct substitution again from here, and we don't get a value yet, we actually still get the infinity over infinity, so we have to do L'Hopital's rule one more time, and then we end up with the limit of a constant, which is just equal to that constant, so our answer is 1 over 7. All right, that is all for today's video. Thank you so much for watching.